In this video, let's find gravitational field to ring. Suppose we have a ring of mass m. Let's try to find out gravitational field to a ring, right, at any point on the axis. Let's take a ring first. Suppose we have a ring, say of radius r, and let's find out the field due to this ring of mass m and radius r at this point P. Let's find out field due to this ring of mass m at a point P. Suppose this point P is lying at a distance of x. Get your point? Okay. So we can see this ring to be consisting of, say, element. Let's consider the element. Let this element is dm. All right, or since I have taken capital M, let me write d capital M. All right, so this is the element. We have considered the element on the ring, and what is the field due to this dm at point P? We already know the field due to, this is radius r. We already know field due to point mass m. So this dm can be considered as a point mass. I can consider dm as a point mass. Get your point? So let's join this first. So the gravitational field due to dm at point P would be in this direction. It would be in this direction, and that would be equal to, this dg would be equal to g dm upon square of this distance. What is this distance? This distance is r square plus x square. All right. So, and this is theta. So this is theta. So this is the gravitational field due to dm in this direction. Now see, the gravitational field to different element would be lying in different direction. For example, if I take dm diametrically opposite over here, then your gravitational field to this dm, the gravitational field to this dm, or let me use dotted pen, that would be in this direction. Gravitational field to this dm is in this direction. But what we are finding out is the gravitational field to this dm and gravitational field to this dm, their vertical component cancel out. For every dm over here, we have a dm. For every dm on the ring, we have a dm diametrically opposite to that, whose vertical component are going to cancel out, and their horizontal component is going to add up. Are you getting a point? For every dm on the ring, we have a dm diametrically on the opposite position, such that their vertical component cancels out and their horizontal component gets added up. So you see, dg cos theta is getting added up, and dg sin theta due to this dm lie in upward direction, and dg sin theta due to this dm lie in downward direction, and they cancel out. So it is only horizontal component which is getting added up. It is only a horizontal component due to all this dm. They will get added up, and vertical component cancelling out in pairs. For every dm over here, we have a dm over here, such that their vertical component will cancel out, and their horizontal component will keep on getting added. So what is added, that is integrated, because integration is operation of summation. If you can add something, you can only integrate those things, right? If you can't add it, can't integrate it. Integration as an operation is operation of summation. So g would be the integral of dg cos theta. So this is g dm r square plus x square. And what is cos theta? Cos theta is x upon, so, and all these x are capital R, they are all same for all the element lying on the ring, so they are constants in a way. So this will be gx 3/2 integral of Tm. So this is gmx 3/2. So that's the field due to this ring, and the direction will be this, of course. This will be the direction of gravitational field due to this ring at any point P is going to be this, where x is distance of point P from the center, and capital R is the radius of the ring. Capital R is the radius of the ring. Alright. Okay, so we have found gravitational field due to ring, right? And what will be gravitational field due to ring at the center? You can see from here, x is 0, so gravitational field at the center will be 0. Moreover, you can understand qualitatively also, you don't need this formula to understand why it is 0 over here. If I take dm over here, the gravitational field will be in this direction, and this dm gravitational field will be in this direction. So gravitational field due to this dm and this dm, they are equal in magnitude but opposite in direction. So gravitational field due to this dm and this dm will cancel out. So net field due to this dm and this dm is 0. And same is true for every pair of element we can take over here. For every element, we have an element on the diametrically opposite side whose gravitational field are going to cancel out. So net gravitational field at this point is 0. This is how you can reason out, right? And on the axis, gravitational field is non-zero. It will be towards the center of, it is towards the center of ring. See, a vector quantity is completely described only when you give its magnitude and direction both. If I just leave over here, then it is not clear. So I must also give you direction, right? Or see that there are two ways of describing direction. One is I can put it in words. The other way is I can put it in terms of vector notation. Suppose somebody want to put it in vector notation, I can take this as x-axis, so y-axis, and so this is z-axis. So your ring is in yz plane. So here write G as, that will be written as gmx and then unit vector in direction of G. Unit vector in direction of G would be minus I cap, right? Minus I cap. This is how we can write. So in that case, you don't need to write this language, because unit vector gives you direction of field, gravitational field. Okay, let's go ahead. Now, since we have found gravitational field due to ring, we can also find out gravitational field due to a disk. Ring is mass distributed only on the circumference. In case of disk, mass is distributed in the whole this region. Mass is continuously distributed over the whole region. So let's attempt that also. Let's try to do that. Gravitational, the topic is gravitational field due to disk of mass m. And if nothing is told, I'll consider this mass m to be uniformly distributed over the disk. I'll consider this mass m to be uniformly distributed over the disk. Let's draw the figure. This is your disk of radius r. Mass is uniformly distributed, and we want to find, say, field on the axis. We want to find field, say, at this point. Point P, and the point P is lying set distance of x. This disk is having radius capital R, and we assume that mass is uniformly distributed. Uniformly distributed means the mass per unit area is constant. So you can say surface density of mass or surface mass density, or surface density of mass, which is denoted by sigma, is capital M upon area of the disk. Getting a point? And we want to find out gravitational field at point P. So see, right now, till now, what we have the information about gravitational field due to a point mass, and we have just found gravitational field due to a ring. Gravitational field due to a ring, which is this one, right? So we have just found gravitational field due to a ring. So we can make use of that fact. We can make use of this expression that we have found for the ring. What I can do is, I can consider this disk to be made up of rings. We can consider this disk to be made up of rings. We can consider element of the disk in the form of ring. We can imagine, we can talk about an element. Let us consider disk to be made up of element in the form of ring of radius x. No, we can't choose x because x is already taken. So let's take a ring of radius r. Let's take a ring of radius r and thickness dr. Let's take a ring of radius r and thickness dr. Let's take a ring of radius r and thickness dr. What would be the mass of this ring? The area of this ring? Area of this ring is 2 pi r dr, and into sigma will give you the mass of ring. So this is 2 pi sigma r dr. Alright, and gravitational field due to this ring at point P will be in this direction. We can make use of the formula that we have just derived. This is the formula: gmx by r square plus x square under root 3 by 2, to the power 3 by 2. We can make use of it. So this is going to be, we can make use of it, and we can say dg is g dmx upon radius of a ring 3 by 2. Yes. So the value of dm is what? G 2 pi sigma, or it's better if I just put the value of sigma over here, 2 pi m by pi r square r dr. So this is going to be what? 2m by pi r square r dr. Or you can put it later on also. Just keep it like this only. Or you can put this value. So 2 pi sigma x r dr r square x square 3 by 2. So we have taken this disk, we have considered this disk to be made up of an element in the form of ring. So I have taken this ring of radius r and thickness dr. If I take a ring over here, a bigger ring, or a ring is smaller than this or smaller than this, then the gravitational field due to all these rings will be in same direction. And since gravitational field due to all the rings, wherever I take it on the disk, they will lie in same direction. So I can simply integrate this dg. since dg due to all the elements are lying in same direction, so in order to get the net gravitational field, I can simply integrate the magnitude. See, when vectors are lying in same direction, then you get the magnitude of resultant vector by just adding the magnitude of each vector. That's what we are using over here. So this will be g 2 pi sigma x rdr upon 3 by 2. All this is 2 pi g sigma x is also constant for all the elements for the whole disk, and this r is variable, right? So this is dr, and r goes from 0 to capital R. I think it is clear. Yeah, so let's take r equals to, or we have rdr over here. Let's take r square plus x square as t square. So in this case rdr will be t dt, right? So this is 2 pi g sigma x t dt upon tq, 2 pi 1 by t square dt is what? Minus 1 by t, or this will be minus under root 0 to capital R, or this can be written as 2 pi g sigma x 1 upon what? X minus 1 upon. You can write like this, or sigma ultimately the value has to be put 2 pi g, and sigma is m upon pi r square x. Okay, so this pi will cancel out, so this will be 2g m by r square 1 minus x upon this value. This is going to be g. So that's the gravitational field to a disk. I can put it in better form. Say the one way to put it in better form. Say, what is this quantity? If I join this point P to the periphery and call this theta, then this is cos theta. So that will simply help you in remembering this. 1 minus cos theta. Okay, so this is how you can keep it in your mind. 2gm by r square 1 minus cos theta. Okay.